In this video, I'm going to try and get through 41 and 42 on page 216. And these are curve sketching problems for trig functions. So first, what we're going to try and accomplish is we're going to try and determine, before we sketch the curve, we want to be able to also identify through first and second derivative, we want to identify intervals increase, decrease, relative extrema, intervals concave up, concave down, point of inflection, and then from there be able to sketch our curve based off of our sine line for increase, decrease, and concavity as well. Okay, so first we look at our function y is equal to 2x minus tangent of x. Okay, let's consider properties about tangent of x. We know that there's a vertical asymptote at negative pi over 2 and at pi over 2, and that is also going to be the restriction for our domain as well. Okay, so first thing, we want to identify where the graph is increasing, decreasing, so we look to our first derivative. Okay, 2x becomes 2, tangent x becomes secant squared x. Okay, once we find our derivative, to find our critical points, we set our derivative equal to 0. And maybe it's easier to deal with secant squared x if we convert it to cosine squared x. So we can think of our derivative is equal to 2 minus 1 over cosine squared x. We can set 2 equal to, in this case, 1 over cosine squared x, cross multiply, and you're going to get cosine squared x is equal to 1/2. And if we solve for cosine, cosine of x is therefore equal to square root of 1/2, which can be written as plus or minus square root of 2 over 2. Okay? And then from there, we can say that x is equal to negative pi over 4 and pi over 4. Okay? We have to restrict ourselves between the fourth quadrant and the first quadrant simply because of our domain. So cosine will have positive square root of 2 over 2 in the first quadrant, and also square root of 2 over 2 in the fourth quadrant, which is in this case negative pi over 4. Okay. So we can create our sine line with our intervals starting at negative pi over 2 all the way to pi over 2, because we have our restrictions here. Our domain is from negative pi over 2 to pi over 2. Pi over 4, negative pi over 4 and pi over 4. Okay, so now we have to test these intervals with our derivative. Okay, I'm going to test it with 2 minus 1 over cosine squared x. Maybe it's a little bit easier to deal or to think in terms of cosine than sine, than secant. So here, if I choose a value between negative pi over 2 and negative pi over 4, I can choose negative pi over 3. Okay, so I have the work shown over here. Okay. If I plug negative pi over 3 in for x, I'm going to get 2 minus 1 over cosine squared and negative pi over 3. Now, cosine of pi over 3 is going to be 1/2, or a cosine of negative pi over 3 is going to be 1/2. Same thing as cosine of 5 pi over 3. And that will be 1 over cosine of pi over 3 is 1/2, and 1/2 squared is 1/4, but that's in the denominator, so when we flip it, that becomes 2 minus 4, which is a negative 2. So we know that's going to be a negative. If I plug in 0 into the derivative, I'll get 2 minus 1 over 1, which is going to be positive. Okay. If I plug in pi over 3, I'm going to get the same result here. I'll get a negative value, so I know that in this interval, my graph is going to be decreasing. Okay. So I can write my intervals, decrease and increase, okay, purely based off of the sine line. Decreasing in this interval, decreasing in this interval, so I write that. And then also our because statements, because f prime is negative. Okay. Increasing in this interval from negative pi over 4 to pi over 4, because in this case f prime is positive. Now, based off of the sine line, we can tell that at negative power of 4, we can get a relative minimum. At power of 4, we get a relative max because of the change in slope. So we can say relative max at power of 4 because f prime changes from positive to negative. Now, if I want to find my ordered pair for my relative max, I can plug power of 4 back into my original equation. And I have that work over here on the right side. So power of 4 into the original function. 2 times power of 4 minus tangent of power of 4. So this is plugging power of 4 into my original equation, right? 2x minus tangent of x. This reduces to be power over 2 minus 1. Tangent of power of 4 is 1. Power over 2 minus 1. We know rough estimate pi is 3, right? So 3 halves is 1.5. 1.5 minus 1 is roughly going to be about 0.5. Right? But we're going to put an exact value for our relative max here. Relative min, by looking at the arrows, we can tell relative min is going to occur at negative power of 4. Plug negative power of 4 into your original equation again. In this case, you'll get negative power of 2 plus 1. Okay. I have the work shown here. All right. 2 negative power of 4 minus tangent negative power of 4. Okay. That'll get you to negative 0.5. So we know that there's relative min because f prime changes from negative to positive. Okay, so now we're done with f prime. Let's move on to our second derivative so we can determine concavity and point of inflection. I'm going to think of y prime in terms of secant, just so that I can go through chain rule instead of having to go through quotient rule. So I'm going to work with 2 minus secant x squared. I want to put that 2 outside the bracket to indicate that there's a chain rule portion that's going to occur. So we go through our derivative. 2 goes to 0. I left that out. And then negative secant squared, right? I got to take the, go through chain rule, bring down the 2, and the negative stays. So negative 2 secant x, okay, multiplied. Now we got to multiply by the derivative of secant x, which is secant tangent x. I want to try to convert this into sine and cosine. Makes it easier to look for critical points. So secant, I made it 1 over cosine, tangent sine over cosine. Combine all this. My second derivative is negative 2 sine of x over cosine cubed of x. So x equals, we can set the numerator and denominator equal to 0 to find our critical points. So I set negative 2 sine x equals 0. X equals 0, pi and negative pi. I am only dealing with the first and fourth quadrant. Cosine pi x equals 0, so cosine x equals 0. X will occur at power over 2 and negative power over 2. However, my domain is between negative power over 2 and power over 2, between the open intervals from negative power over 2 and power over 2. So all these values are going to be out. Okay, so power over 2 is out, negative power over 2 is out, pi is out, negative pi is out. Pi is out. All these values are outside of our domain. The only critical point that's inside our domain is 0. So we have our endpoints at negative power over 2 and pi over 2, and at 0. So we need to determine whether it is concave up or concave down in these intervals. So I can choose a value between 0 and negative power over 2. I can choose negative power over 4, for instance. Right? In the fourth quadrant, sine will be negative. In the fourth quadrant, cosine is going to be positive. So negative times negative is positive over positive is positive. Okay. Here, this is first quadrant between 0 and power over 2. I can choose power over 4. But I know that sine of power over 4, right, anything in the first quadrant, sine and cosine will produce positive values. Okay, so positive here, but this is positive times negative. So negative times positive is negative. Negative over positive is negative, so I know there's concave. The graph will be concave down here. Changing concavity, so I know there's a point of inflection at 0. Okay. So now I know concave up in this interval because f double prime is positive, concave down in this interval because f double prime is negative. Point of inflection, plug 0 back into the original equation. I'll get 0 minus 0, which is 0. So that's my point of inflection. So based off of all that, I can sketch my curve. Okay, 0, 0 point of inflection. Negative pi over 4, negative 0.5 is the relative min. Pi over 4.5 is relative max. Decreasing concave up, increasing concave up, increasing concave down, and decreasing concave down.